Very good afternoon to all present, to all the participants. This is the last lecture of the session, and the topic is machine learning through Google Earth Engine. So in this course, you have seen from the starting basics of remote sensing, then basic machine learning, then artificial neural networks, CNN, and then some deep learning and GAN and so on. So in my session, I'll follow a similar flow. I will give very brief on, so it should be a self-contained session. It's very brief on machine learning. What are the different applications in machine learning? What are some of the works that we have done at IIRS? And then I'll move on to Google Earth Engine. What it is, what are the functionalities available in Google Earth Engine, and what are some of the studies that have been done using Earth Engine. So my name is Prasun. I am with the Geoinformatics department here at IIRS. So you must have seen this image before. The AI, ML, DL, these are not new terms. These have been around for well over 50 or 60 years. And initially it was when the term AI was coined, it was primarily of theoretical interest. And with computers and this becoming popular and data being available, people started doing machine learning. Then there was a lull phase, and then finally when GPUs and these faster computers were available, deep learning applications and these evolved. And you have seen several applications of AI. Some very good ones are shown on this slide. Like computers playing games like chess and AlphaGo, computers driving cars like self-driving cars, and then these highly dynamic and intelligent robots which can do things like home deliver your e-commerce packages and several other things. So, but all these are very general purpose AI applications. We are in this course we are focusing on things that you could do with AI, ML, DL on remote sensing. So these are some general applications of DL. Self-driving cars, identifying and segmenting individual objects like cars, bicycles, roads, buildings, people, and so on. This application, so one of the lecturers yesterday said that your mobile phone is a very important and very advanced application of deep learning. It can identify, whenever you take out a camera, it can identify bounding boxes of faces. Not only that, along with that, the name of the person by looking at the gallery and existing images. Several applications based on images, videos are already developed. So this is one application where Google Translate, you can use Google Translate to take a photograph of some text which is not in English, and then it will first segment the letters, do an OCR kind of processing, optical character recognition, and then convert it to text, and then translate that text into English. So these are very important applications when you are doing things like when you're in foreign countries and you don't have text which is in English. Not only that, there are newer initiatives like OpenAI, which want to achieve general purpose intelligence. So you could draw a simple image in paint with some grass and some water body, and it will try to synthesize or create a painting type image by looking at existing paintings by these very famous artists and try to draw something similar out of a hand sketch or a very simple sketch drawing. So these are all general purpose applications. What we want to do basically is to apply it to remote sensing. So we don't want to only look at images and tell whether it is a cat or a dog, or whether the image that you see on the top is an airplane, but rather look at a satellite image or look at a drone image or an aerial image and be able to classify several classes. It could be land cover. One of the very most common initial applications that people develop is land cover, whether it is agriculture, whether it is forest, whether it is urban settlement or a water body, to as complex as whether this is a car, and if this is a car, whether it is a passenger car or a commercial vehicle, or whether it is by looking at the pattern in which it is being driven, whether there is a probability of an accident occurring and things like that. So there are very vast number of applications. Depends on what is the data and what we are trying to achieve. So this is a slide which shows these images at the bottom show that how from a very high resolution image where you can identify cars and all, you can make you can use machine learning and develop a map like this, which will have each pixel will have an attribute or a class assigned to it. That pixel could be a car, it could be buildings, could be trees, low vegetation, and so on. So there are multiple applications of image classification. I will show you some of the so I will show you some of the applications that we have developed using these technologies and using remote sensing or Earth observation data. So how's machine learning defined? Machine learning is a field of study. Arthur Samuel gave this definition in 1959. Where he said that it's a field of study that gives computers the ability to learn without being explicitly programmed. So when you are learning a new computer language, first thing you do is print hello world. So you're explicitly telling the computer that you have to print the word hello, to print the text hello world. Then you add two numbers or you find prime numbers. So you're telling the computer what it has to do. Whereas in a general purpose machine learning algorithm or a computer should be able to look at data and understand what it has to do. For example, you give it 1,000 images of cats and tell it is a cat, and then it sees a new image and it should be able to tell whether it is a cat or whether it is a cupcake. So that is what machine learning is. There are more definitions of machine learning. Tom Mitchell gave this in recently in 1998, and he said that machine learning is the study of algorithms that improve their performance at some task T with experience E. So a task T, now let's take a very simple example. Let's take playing chess. Now, more, machine learning program, more this number of examples that it sees of games being played, it learns and learns from them, and then it improves its performance. So you name it, Deep Blue or AlphaGo, or to play games against humans, they learned by looking at other games being played. There are many examples on the internet. If you look, there are these programs which you play some simple game like Pac-Man or pinball or something, and the computer just looks at the video of you playing the game and it learns what it has to do, and then it and then it plays the game itself, beating the computer. So these are different definitions of machine learning. And as the course has been structured very nicely, machine learning actually involves these three big components. One is unsupervised learning, supervised learning, and reinforcement learning. Unsupervised learning primarily being clustering, or where you don't specify or you don't give the training data, rather you just tell that these are the number of clusters or these are the number of end results that I want, and it segments or creates these clusters. So clustering these clustering algorithms can have multiple real world applications like targeted marketing, recommender systems. You search anything on Amazon or Flipkart or these online apps, and at the bottom you'll see things like these are suggested products, or people who also searched this also saw these things. So these are coming from unsupervised learning algorithms. So there are a million products on a e-commerce website, and uh, you search through hundreds of them. Some person looks at another hundreds of them. A new third person comes in and he picks up an item A, so it falls in which cluster. According to that, these e-commerce websites, they they provide recommendations as to, since you belong to this cluster 1, so you are most likely to buy these other 99 products. So that is how clustering works. You have a lot of data and you create these clusters, and there are several applications. It could be a recommender system, it could be segmentation, marketing, and so on. Another subcategory of unsupervised learning is dimensionality reduction. Initially, ICA, PCA, these have been very popular. Recently, with machine learning, with more advanced algorithms, we are able to further compress the data, further only extract the data which can give us meaningful results. Then if we have training data, we will you use supervised learning. You do regression or you do classification. That is, you find the classes. A very good example is fraud detection. So just by looking at, so sometimes you do payments through credit cards or UPI, and 1 out of 10 times it gets rejected. Now, why is it getting rejected? They say it is a network issue. Actually, they have these fraud detection algorithms which looks at patterns. So you are in a city and you're making payments regularly around that area, and suddenly it finds a payment being made in somewhere in Nigeria or some other country. So so it detects that that person could not have traveled in such a short time to another country, and it is possibly a fraud payment. So these kind of fraud detection algorithms classifies data based on existing data available. So you need training data for supervised learning, and finally reinforcement learning. Lot of content was delivered on reinforcement learning also. Things like giving reward and then improving the algorithms to do certain tasks like take decisions in real time or play a game and stuff like that. To do all these gamut of tasks, there are several hundreds of technologies out there in the market today. A lot of them are open source. You need not pay any money to purchase these or to download and use these softwares and build your own machine learning models. But again, there are an equivalent set of softwares that are in the closed source domain, the proprietary domain, uh, and possibly equivalent to what is there in the open source domain. So a lot of these terms may be known to you. Things like TensorFlow, Keras, PyTorch, Skitlearn, Caffe, OpenAI, Theano, and so on. Vika is a very interesting package which we use. Even Earth Engine uses. then PyTorch, and so on. And so there are these gamut of technologies in the market available today. A lot of people first target TensorFlow and start learning, and it is a very steep learning curve. So if you've not done any machine learning ever, I would not suggest you start with TensorFlow. Rather, take up Python, which is a general purpose programming language, which is easy, has a slow learning curve, and then adopt this package called skitlearn, which does most of the things that you want to do. Once you get hands dirty and you start understanding things, then you can go to packages like Keras and Cafe and TF and things like that. Okay, so using these technologies, we can build several applications with remote sensing data. Now, remote sensing or Earth observation data is fantastic data set which can be used for multitude of applications. This animation just shows one of the products derived from an Indian satellite, a sensor on an Indian satellite called Ocean Color Monitor, or OCM, that is there on a satellite called OceanSat-2. And this product has been made at every 15 days, and this is called an NDVI. So the green color basically tells you the greenness of that area, or you could correlate that to the crop being grown in that area. And the red or the orange color basically says the barrenness, basically no crop in that area. Now, if you look at the dates, the months, you will be able to correlate that during the Indian summer monsoon season, that is June, July, August, September, when you have a lot of rainfall throughout the country, the entire country goes green, whereas in the non-monsoon season, only the northern belt, the Indo-Gangetic plain, so has greenness because of the perennial rivers and a good irrigation system. The large parts of South India are still there is this data available freely in open source domain. You can look at the Bhuvan website and download this data. And now machine learning or deep learning, these are data intensive applications. You require a lot of data to build a model. And remote sensing is an ideal way to generate a lot of data. So remote sensing gives you data in some cases every day, in some meteorological cases even every hour. So you have all this data at very fine spatial resolution, at a high frequency temporal resolution. So, and you can use all this data to build your own machine learning models. So this is first study that I want to show that we did using remote sensing data. Some of the data was consumed or was downloaded from Earth Engine, but the study was done on Python on a desktop-based system, or you could use Google Colab or something. So the idea is this remote sensing derived product called NDVI that I showed you in the previous animation, which shows the greenness of an area. If you plot that greenness, it is like a sinusoidal curve. So basically, this is this area somewhere in Haryana where they have a very continuous two crop cycle thing happening. So they grow either rice in one season and wheat in one season, and then they repeat that year after year. So if you take a long-term data like 10 years or 15 years, you will see these curves very nicely in the data set. And if there is improvement, so in the rest of the part of the country where there is less water or some other local issues, there either only one crop is happening, So with improved irrigation, improved crop management practices, you can see this curve from single in the whole year to two curves or two peaks or three peaks even in some cases. So we did this study over Punjab, and we saw this yellow color basically shows that uh, these are the pixels where two crops are grown. The rice wheat cycle is happening throughout Punjab. The northern part has some forests, but recently, due to some improved practices, some places around Amritsar, they have started growing three crops. So this kind of uh, uh, intelligence can be derived using remote sensing data uh, for each pixel, not only take like 256 by 256 image slices and give an attribute to it. Rather, for each pixel, take the entire temporal values for each month, each 15-day period, what is the value, and then do some learning based on the type of the crop. So you can find out not only number of crops, you could possibly find out the type of the crop, uh, whether it is under stress, whether there is any adverse event happening, whether there is a whether the NDVI curve is following the trend and not, and if there is a drought which is predicted and things like that. So a lot of these applications are already made by ISRO. You can look at the Vedas site made by SAT, where they've done this on a very large scale, uh, and you can explore that. Uh, a very common popular application these days is counting trees using deep learning or machine learning. So basic idea is you create these image slices and then you assign a value, whether the tree is present or whether it is absent. And so this first thing is it requires very high resolution data, something like spatial resolution of 0.5 meters. Now 0.5 meter data is not generally freely available. So you could use Google Maps data, or you could purchase it from these different high resolution data providers, even Indian satellite data, and build this training data. So we took a part in North Karnataka and we created these image slices of 64 by 64 pixels, and then we created this training data of these 1300 images of whether it contains a tree crown, as in whether it contains a complete tree, or whether it does not contain, whether it is barren. And it was attempted with multiple models and different types of training data and all that. And so what we were able to do is come up with a very accurate count of trees. This has many applications. So I think I have a small animation here. So here what you're seeing is a video fly through, which kind of mimics UAV data. It is not actually mimic. But what is interesting is at the bottom of the screen, if you see, it says tree count 0. In this area, there are no trees. And as soon as the video moves forward, where more trees are coming, you see that the tree count is increased. This is although not perfect. We are only looking at RGB images, that is uh, in the optical range. What should have been done is we should take the IR band, the NIR band, because any other green object like a green terrace or a green field also may appear as one or more trees. So this is a lot of things are under research. We are trying to make these algorithms better by either improving the model itself or by increasing the amount of training data. This is another classical example of large amounts of training data available freely. You can look this up, DeepSat image repository. what they have done is they've used this NIPE dataset, National Agricultural Program, which runs in the United States, and that data is available freely for the continental US at a very high resolution data is there, and that data has been made into slices, and a value has been assigned to it, like this is a water body, this is a road, this is a tree, this is a building, and so on. So we took that data and we then trained our own version of models based on existing models like ConNet and AlexNet and VGG. And then we tried to mimic the same for Indian cities. So we took different parts of different cities, Hyderabad, Bangalore, Delhi, Calcutta, Mumbai, and so on. And using a data set, which is called the Indian Atlas project, we tried to train the data into urban built up or rural built up, rural open space, urban open space, and so on. But we didn't get very good results. Why is that? Now, it is not only the spectra or the image, or in remote sensing, you have other objective factors. For example, if you are predicting how the city is growing, the factors are different in each city. For some cities, it is the roads, wherever new highways or the metro rail is expanding or the roads are expanding, that is where the urban areas increase. But in some cities, for example, Kochi in Kerala, their cities expand along the waterways, along the backwaters. So for each city, they have their own specific conditions, and blindly entering data and training a model doesn't serve the purpose many a times. I think some applications were shown on cloud detection. This is also some work we did on cloud detection. And this is very pertinent application, because if you happen to go to USGS to download any Landsat data, you would clearly see for each tile, they say that this is the land cover or cloud cover percentage. Now, where is this number coming from? 54 point, so such a precise number. 54.2% of the scene is covered by clouds, whereas the same is not available currently on the Indian data ordering portal. So to do this, we also explored using CNN on convolutional neural networks on how we can detect clouds. So we found out that it is not only the clouds which are the problem. The clouds, the shadow it casts on the ground, cloud shadow. In hilly areas, especially in Himalayas, there is snow. So both are looking white. So how do you differentiate between a cloud which is white and snow which is white? So there is snow. So this image in the first shows a false color composite. False color composites are ways where you can rearrange bands to emphasize certain features. So we've created a false color composite where the snow looks blue and the cloud looks white and the rest of the barren areas look brown. So you can clearly see in a normal optical image, the RGB image, you would see all of this as white. So it is, and if I say no, all of this is white, let's mask everything out, you are losing important information on snow cover. Snow cover is a very important information for things like water management, reservoir planning, and so on. So we created a reference data set first, and then we applied different models like random forest, CNN, and FCNN, CloudSNet. So a lot of architectures were applied. Roughly 3 publications came out of it, one includes an IEEE. And what we concluded is that it is a very difficult job, and it also includes more factors. For example, haze. In winters in the entire northern plains, you have this haze, and specifically at the time when there is a satellite overpass. So most of the images appear white, but those are not clouds. So how you could take correct masking is very important thing which we can solve using machine learning. This is another important study that we did on using nighttime lights. This is another data set which a lot of people are not aware about. Satellites also take images at night. And in those images, you probably cannot see individual cars, but you can see city lights. So this is our small portion of uh, uh, Maharashtra. These are the two towns, Sangli and Kolhapur. On a normal false color composite image, this is from Sentinel-2, and this is at 10-meter spatial resolution. So you can see individual water bodies, urban areas, forests, and agriculture, and so on. But at 1 kilometer or 500 spatial resolution, you cannot see these individual things. But what you can see is lights. You can see electrification happening. If I have long-term nighttime light data, I can use it as a proxy for economic development, to study socio-economic development, to study population growth, to study demographic indicators, so many things. So one data set called the DMSP OLS, this is available from United States Air Force and NOAA. They've built this product, which is available from 1992 onwards till 2013. And then the VIRS DNV, this is another satellite with another sensor called the day-night band. This is available from 2013 onwards. So these are at different spatial resolutions. This is at 1 kilometer, this is at 500 meters. But I want to do a long-term study. I need all this data to be harmonized. They all should be at the same resolution and they should be comparable. So a data set from 2000 from one sensor should be comparable with data with 2020 image from another sensor. So we use machine learning to intercalibrate these data sets so that these data sets are harmonized and they can talk to each other. And these are so we used a lot of what you call as input features in machine learning, but these features were created using remote sensing and other data sets like land use, land cover, digital elevation models, slope, road network. This is from the OpenStreetMap data, road density, distance to road. So using GIS, using remote sensing, using open data, we were able to create a machine learning based regression model which can convert a 1 kilometer nightlight data to a 500-meter nightlight data. And using this, we are able to create a long-term time series data from the year 2004 till 2013, and then the IIRS, which is available till today, has been merged to create a very long-term time series data. This can be used to study development, electrification, uh, and so many. There are many studies which also uses such data sets to study conflicts, migration. Lights are going out some places. Why? Forest fires, oil fires, so many different things. But these are all applications that we have taken the data from Google Earth Engine or from other sources and have developed it on Python or these languages on local systems or desktops or servers, or in some cases Google Colab kind online applications. Now a new tool, a relatively new tool has come up called the Google Earth Engine. And what is this? This basically is a online platform which allows you to work on large amounts of remote sensing data. Okay, so it is basically a single place where all this remote sensing data is available, and you have also the Google's power to process all this data. Okay, So, but thing is, it like other machine learning things that people are learning today, it is all programmatically based. There is no like a software where you can click and get your output. Rather, it is a programming interface. The primary programming interface which is available on a browser, it is on the Java. It is on a flavor of JavaScript language, and it has APIs in Python also. So this Earth Engine thing has roughly 17 petabytes of data. This figure I got from an earlier slide, so probably this has increased by now. And this data is increasing every day because these satellites are continuously covering the Earth continuously. So roughly 4,000 new images get ingested into this Google Earth Engine platform every day. So Earth Engine, apart from the data, it has several algorithms, several data types, operators, which are built to use this data. So, and this is such a scalable thing that you don't need to like download any data. You just write code to select the data, select the operators that you want to apply, and get your outputs on the fly. And you can just simply zoom out and run the same thing on the whole globe. So how does it work on the whole globe? Imagine downloading data for the whole globe on your system. It will take ages to download it, another few ages to process it, and then create a meaningful result. So how does Earth Engine do it? So Earth Engine has two computation modes. First and the most important is on-demand computation. So on-demand computation basically means there's another term called lazy execution. So what it does, it only executes something when you want to see a result. Okay. So for example, you want to see a new output, you want to download a new file, or you want to plot a new graph. Only then Earth Engine processes the program. Otherwise, it doesn't do anything. So it's also called they also call it a just-in-time map tile renderer. So if you close the map window, there's nothing happening. If you open the output map window, only then the program runs. So it only runs for the area that you're viewing. It doesn't run for the whole globe. And when you zoom out, it runs for additionally for that new area which has come up, and so on. So that is how it saves on the processing speed, on the time required, and the resources required to run that kind of application. It also runs a lot of download tasks like batch computation. There it uses the popular MapReduce concept to process all this data. So we've done a lot of work. A lot of people are doing a lot of work using Earth Engine. This is an earlier work. This doesn't use machine learning per se, but this is a very important work with respect to how large amounts of data can be used to come up with actionable intelligence. So this is a study area in Uttar Pradesh between which is near to the city of Lucknow. This is the river Ghagar, and it is infamous because it continuously changes its path. So if we have the entire data set like Landsat, MODIS, Sentinel from way as long back as 1980s onward, and if we can create a simple NDWI, a water index, and merge all the data, we should be able to find out the probability of water happening at each pixel. So if it is a stagnant permanent water body, there's 100% probability. But if the river course is changing, the probability of water being at a pixel is the number of times the river happens to be at that course. Now, since the river is changing, it is advised that people should not live near the banks and so on. So these inputs are regularly given to decision makers, and there's a very there are large projects like the National Geomorphological Map and Lineament Mapping Project, which maps the entire active floodplain, the older floodplain, older alluvial plain. But these are uh, like scientific outputs, not directly transferable into actionable intelligence. But whereas if you take all that remote sensing data, create the NDWI, merge them, and create a probability map like this, and tell that in the past 40 years, this is the places where the river has been to, and it is very dangerous to create a house or a infrastructure here, because we never know in the next few years the river may come back. So Earth Engine provides this power to create such kind of an application, and really quickly. You don't need to download anything, you just need to write code and see the output on the browser itself. Now we come to the core part of the thing, is how you do machine learning on Earth Engine. Now, Earth Engine provides some inbuilt functions. As I said, it is a programming-based interface, so you have to write code to do machine learning on Earth Engine. So for unsupervised classification, like clustering, there is things like k-means, efficient k-means called x-means, some algorithm called linear vector quantization, and so on. So there are some inbuilt clustering algorithms built in Earth Engine. Also, there is supervised classification classifiers available, like decision tree, random forest, support vector machine, card, naive Bayes, even Maxent recently. I think this has come up recently because this was not there earlier. But you feel limited by these algorithms. Bas itna hi, what if I want to make my own model, like create these layers, neural networks and dropout layers and things like that. So what do we do then? How do I integrate more complex machine learning models? So to do that, Earth Engine provides interface with TensorFlow using a function called EE model. So the best part comes here. These models are developed and trained outside Earth. So Earth Engine only, when you're working with TensorFlow, works as a data provider. Okay, it provides methods for exporting training testing data. So you want a huge chunk of remote sensing data to be applied to a model. So this Earth Engine will only allow you, or will allow you to package the data into something called TF records or TensorFlow record format, which can be directly read into TensorFlow. So you have to download this and then use it again on your system. Now you're not on Google's cloud infrastructure where you can use high performance computing and stuff like that. So Google API allows you to export the data into TF record. You can develop your own pipelines or your own complex models in TensorFlow and run with this model which you get from GE. There are a lot of examples available, mostly using Python. You could optionally deploy this machine learning application on the Google AI platform. So Google Cloud allows you to directly fetch the data from Earth Engine, apply it on TensorFlow on their platform and get the outputs quickly. But that requires money. So till this part, that is working with JavaScript and getting it on your computer, is all free. But the last part, where you to run TensorFlow models and integrate it with the Earth Engine, that part requires a billable credit card. Finally, to test all this accuracy, it also has a class called EE.confusion matrix, and it also has provisions to do hyperparameter tuning and so on. And since it is so fast, you can run your models quickly change the hyperparameters and see the outputs very fast. So that is very easy and quick to do on Earth Engine. So there are two studies that I want to show that we did using machine learning and Earth Engine. So this is basically land cover classification over the Dehradun district, and this was published recently in 2021 on in remote sensing, where we've tried to not only see, so we've used all the Earth Engine power, we've used all the data, remote multi-temporal remote sensing data, we've used all the inbuilt algorithms, we've even extended the algorithm. So we built a new algorithm, or not a new algorithm, we've built an algorithm from support vector machines. We built a new thing called relevant vector machine on Python. And so since we have all this set up, we can even explore more things, like what is the importance of sample design, where you should be collecting your training samples, what is the correct sample size, how many points do you require to train the data or to verify the results, what is the effect of the quality of this data. Sometimes there is error in data collection also. So what is the effect of that on, so Earth Engine gives us the entire power of data and machine learning. So we can now emphasize on the science, on the important statistics, the important things that influence the outputs of machine learning classifiers. The second study that we did on Earth Engine is a very interesting topic called seagrass mapping. Here we used Landsat and Sentinel data to see in this southern tip of India, the Park Bay, there's a very large reserve underground forests of seagrass where some exotic species like sea elephants and they reside, and they are very important for things like climate and ecological balance and so on. So we've tried to implement these different classifiers like SPM, CART, RF, and we were able to quickly generate these outputs, these seagrass maps, and we also implemented things like pixel-based and object-based classification and all that on Earth Engine. So Earth Engine not only provides you data, not only provides you classifiers, it also provides you an entire programming language where you can build your own things. So you can use JavaScript or Python to build your own algorithms, build your own methodology in Earth Engine itself. So Earth Engine is a very popular and a very strong, powerful software. But as this XKCD image says, that sometimes a lot of things get unnecessarily complicated. So there are two characters which are talking. One says, I just want to find out whether in a given photograph there is a bird or not. And this lady says that will need research, that will need a research team and at least 5 years of work. So finally, I would like to stop here because we have another session immediately after this, and I can take few questions. And I want to say that right now what we are doing is completely uncharted territory. This is very interesting. This is a view of the Earth when Marco Polo did his extensive journeys across the oceans in around 1250 to 1300. He saw that Earth would look like this. There would be Persia here and Egypt here and Middle India here and India here and so on. But actually Earth doesn't look like this. So what we are doing today is uncharted territory. We are looking at things at a certain way, but tomorrow if you learn and if you adapt and you build your own applications, you will come across newer discoveries, newer things, and it may not look like things that I have developed or things that we are developing right now. It could be something absolutely new. So AI is a completely new area, and applications in remote sensing and Earth observation is something that we are looking forward to, and we do a lot of it at IIRS. So that is, if you are interested in any of these, you request you to go to our website, look at our course calendar, look at different courses that we do here, and that is it. So it's about 4:40 now. If we have any questions, we can take it now. Otherwise, please be present at 5 o'clock. We will have with us Dr. Uma Maheshwaran, who is the Scientific Secretary of Indian Space Research Organization, as the chief guest for the valedictory function. So if you have any questions, I'd be happy to take now. And please be present at the valedictory session at 5 p.m. So great, we're already getting a lot of questions. So the first question is very interesting. First question says, can we reduce the bit depth of satellite images and just select the required bands for analysis? It's a very interesting question, and it actually has two parts. First part is one second, I should. So the first part is, can we reduce the bit depth? Now, what is bit depth? Now, so what I am not getting the name of the person who was asked. What he or she is asking is, we want to reduce the radiometric resolution of the satellite data. That is why you need to understand remote sensing and Earth observation more, and also you need to understand machine learning. So there are two different branches, and you need to understand both very clearly to merge these two sciences. So remote sensing or Earth observation data, or the satellite images, they come as bands, and each band, in layman terms, will have some data type. Data type meaning it would be integer or float or double or long, as you know it in programming languages, but we call it as, it is either 6-bit or 8-bit or 16-bit. So normal RGB images that your camera phone takes or your digital camera takes are 8-bit images. So the values range from 0 to 255 only. But satellite takes images, a lot of these new age satellites take at very high radiometric resolution, even up to 16, even 24 bits. So you have this data which traditional libraries like OpenCV cannot handle. So you need to use libraries, Python libraries or tools to reduce the data to a certain level. That is, you're basically killing the data. You are removing important parts and using only the data, only the bit depth that you can handle. For example, OpenCV can only handle 8-bit images. So you have to reduce it. Now, how do you reduce it? So there are different libraries, and that will take another session. So yeah, look up for satellite image processing libraries, and you will get your answer. Also, you can reduce. So the second part of the question is, should we reduce the bands? Yes, you should reduce the bands. That is where dimensionality reduction comes in. You have different algorithms to reduce the number of bands, so that you only have the important bands where you can extract the most information. Okay. So again, a lot of remote sensing is involved. is there a Indian remote sensing classification data set like uh, the one I showed? I think they're referring to as UCM. So remote sensing classification data set, I may not be aware currently, but a lot of Indian remote sensing data is available freely to you. So I hope you all know of Bhuvan, Bhuvan. Just Google it up. There's a website which is made by ISRO, which gives away a lot of cloud-free Indian remote sensing data for free. It may not be current, you may not get yesterday's data or today's data, but there is lot of long time period, lot of data, time series data available uh, on that website. Search for Open Data Archive and you will get all that data. You can use that to build your own models. Share with me. How is the photo taken by satellite so clearly? So there is a lot of engineering involved, a lot of scientists involved, a lot of engineers involved, which make optics, uh, cameras, which are in space 700, 800 kilometers, even some cases 30,000 kilometers above, and uh, take these images. Once they take the images, there's a lot of electronics involved to store the image as a file, then transmit that image to Earth, and then on Earth we have data processing teams which take the data, clean it, make it look accurate, and then give it to users. So a lot of science and engineering goes into it, and that is what space agencies do. That is what ISRO or other space agencies worldwide they do. They create this entire engineering chain where you can get scientific data for different purposes. Will zero padding reduce accuracy? I don't think so. Why I don't think so? Because generally, remote sensing images or tiles are very big, 3,000 or 5,000 pixels by 5,000 pixels. You are making uh, a zero padding of 2 pixels, 9 pixels, even 50 pixels. So 50 pixels in a 5,000 column image, the ratio is very small. So uh, zero padding may affect the corner uh, zones, but if you look at the bigger picture, I don't think it hampers the accuracy of your classification results. Okay, last few questions. Can dimensionality rectification techniques be implemented on satellite images? Yes, and it is a very important part of our syllabus. So whoever asked this, please refer to our course calendar here and look at the different courses that we do. We teach a lot of remote sensing, how these satellite images can be made better, how to reduce its dimensions, how to extract important data uh, and remove redundant data away, and then use this data using different advanced classifiers. Uh, your coordinator, Dr. Anil, is an expert into how you can use these for fuzzy-based classifications. It need not be every time that I can look at a pixel and tell that it is water. It is probably 80% water and 20% of submerged vegetation. So this is a very advanced field and multidisciplinary field in not only involves electronics or statistics or mathematics, it involves basic knowledge about the science of the phenomena that is happening. So we have a lot of people working in different fields together to get this kind of information. How can we use Google Earth to locate population density of a state? Don't use Google Earth. Use you can use Google Earth Engine. There are different data sets called gridded population data, which will tell you the population density of individual pixels. Why only state? The usage of SAS and R tools for satellite imaging techniques. Very good question. So yes, we have a lot of our colleagues, faculty members here. They also use R. R is another open source scientific programming language, uh, which is almost as popular as Python, uh, but has a niche audience. So yes, people are using R also for doing these kind of machine learning and satellite image processing types of works. SAS is a paid software, is a proprietary software. Uh, I have not seen many applications using SAR. Maybe there are, I am not aware. So yeah, because primarily it is a paid thing. So uh, we have a lot of open source thing available. Can early warning signs of earthquake be created using MLDL? Yes, it can be. It's a very interesting application. You've just coined the next PhD of somebody. So yes, I think I should wind up. So yes, detection of earthquakes is possible. A lot of work is being done. You may be probably aware of something called an atmospheric constituent called TEC, total electron content, which has shown promising signs of giving precursors or telling that maybe there is a earthquake impending. Unfortunately, it is at a coarse resolution, about 250 odd kilometers by 250 odd kilometers. Secondly, it is doesn't tell the time when it will occur. It will say it will occur, but when you don't know. So these are some problems with resolution and all, time and space. And yes, machine learning and DL is a very important, can be used as a very important tool to improve the efficiency of these earthquake predictions. So I will now stop. It is 4:50, and we will take a 10 minutes break. And please be available at 5 p.m. for the valedictory function, where we will have Scientific Secretary ISRO as our chief guest. Thank you.